video, we're going to talk about the self-ionization of water. And what this means is if we look at pure water as a liquid, and we're actually going to look at two molecules just to see what's going on here, right? If you have a beaker of pure liquid or pure water sitting on the counter, it's not all H2O, right? What's actually happening is one water molecule here is going to act as the acid, and it's going to lose a hydrogen ion. The other water molecule is going to act as a base, and it's going to accept that hydrogen ion. So what we get is H3O plus as the conjugate acid, the one that's added the hydrogen ion, and hydroxide, the conjugate base, the one that's lost the hydrogen ion. What makes water neutral is the fact that we are making one hydronium, H3O plus, for every one hydroxide. So the amount of acidic components is equal to the amount of basic components. So if you have equal amounts of acids and bases, you have a neutral substance. So this is what water naturally does. And it's very weak. Notice the equilibrium lies strongly to the left or towards the reactants, which is just the liquid water. There's not very much hydronium and hydroxide present, but there is some. So here we're going to write the Kw. So we have had Ka, Kb. Here we have Kw. So this is the equilibrium constant expression for this water self-ionization. So again, we ignore liquids, which are both of the reactants. So the only thing we have in our equilibrium constant expression are products. Products go on the top. So we've got the concentration of H3O plus times the concentration of hydroxide. If you want to write this over 1, you can, but it's not necessary. Okay. This equilibrium constant has a value of 1 times 10 to the negative 14. It has been experimentally determined that the ratio between hydronium and hydroxide has to give you this value of 1 times 10 to the negative 14. The reason this is helpful is because if we have a substance where we know the concentration of hydronium, we can determine the concentration of hydroxide and vice versa, because we know the two multiplied together always has to equal 1 times 10 to the negative 14th. The reason this is important is this is going to help us determine how acidic or how basic something is. So when the amount of hydronium is equal to the amount of hydroxide, which is what this first image here is trying to show us. So the left-hand side of the graph is the concentration of hydronium, or how much acid there is. The right side is how much base there is. So notice here when the two are equal, they're both equal to 10 to the negative 7th. This is a neutral solution. Right, there's the same amount of acid as there is base. This is what's true for pure water. If I add some acid, so that means I'm going to increase the amount of hydronium. It looks like I'm going down here, but notice 10 to the negative 2nd is bigger than where it started, 10 to the negative 7th. So I've added hydronium, which is the acidic ion. By doing that, if I want to keep that Kw equation true, if I make this H3O plus number bigger, and I still have to equal 1 times 10 to the negative 14th, the hydroxide concentration must go down. And if I make the hydronium up to 10 to the negative 2nd, the hydroxide has to go down to 10 to the negative 12th. Okay? Because there's more hydronium than there is hydroxide, this is an acidic solution. More acid than base. If I instead add hydroxide, or the basic ion, so now I have 10 to the negative 2nd base, it's going to cause the acid, the hydronium, to go down to 10 to the negative 12th. So now I have more base than I have acid, and it's a basic solution. Okay, so the fact that this has to stay balanced, we increase one, we have to decrease the other. And we can mathematically determine how much because we have this equation, and it's an easy to solve equation. So here's an example. We are going to calculate either the hydronium or hydroxide concentration required to make each of the following solutions. All right, and then we're also going to decide whether it's neutral, acidic, or basic. And we're going to do that by deciding, do we have more hydronium making it acidic, or do we have more hydroxide making it basic? So A is telling us we have 1 times 10 to the negative 4th molar hydroxide. So again, that Kw is hydronium, so H3O plus, times hydroxide, has to be equal to 1 times 10 to the negative 14th. So this first one, I know hydroxide, I don't know hydronium. So I'm going to have some unknown number times the hydroxide concentration I know, which is 1 times 10 to the negative 4th. And that has to be equal to 1 times 10 to the negative 14th. So to solve for concentration of H3O plus, we're going to take 1 times 10 to the negative 14th and divide by 1 times 10 to the negative 4th. This is going to equal 1 times 10 to the negative 10th. If you know power of 10 math, great. If you don't, use your calculator, but make sure you're using your calculator correctly. Do this one on your calculator and make sure you get the right answer. And if you don't, please talk to me and I'm happy to help you figure out how to use your calculator properly. So 1 times 10 to the negative 10th is the H3O plus concentration. If I compare that to 1 times 10 to the negative 4th for the hydroxide concentration, I see that hydroxide number is bigger than the hydronium. So hydroxide represents base. So if my base number is bigger than my acid number, this is going to be basic. Next one, I know hydronium concentration, and I'm looking for hydroxide. So the 2 times the hydroxide concentration has to be equal to 1 times 10 to the negative 14th. So hydroxide is going to be equal to 1 times 10 to the negative 14th divided by 2. That is equal to 5 times 10 to the negative 15th. So the 2 for H3O plus is much bigger than the 5 times 10 to the negative 15th for the hydroxide. So this one is going to be acidic.